If you follow automotive engineering, you've probably seen the recent headlines predicting that 2026 is the year of the valveless engine revolution. While the valves themselves remain, the heavy, forged camshaft is being removed from these next-generation designs. For over 100 years, this single piece of steel has dictated exactly how every combustion engine on Earth breathes. It is an entirely analog part. While reliable, a solid spinning piece of metal belongs to an era of manual assembly, creating a bottleneck for modern engineering that relies on high-speed digital processing. To survive strict future emission standards, engineers realized they had to remove this mechanical limitation. Looking at this cross-section, you can see how the physical shape of the camshaft lobe forces the valve springs open. Because the lobe is solid metal, its shape is permanent, locking the engine into one fixed, unchangeable breathing rhythm. This chart highlights the unavoidable engineering compromise. An engine tuned so its efficiency peaks at highway speeds is inherently inefficient when it's idling in stop-and-go traffic. Automakers spent decades developing variable valve timing to stretch these limits. But even the best VVT setups are physically tethered to that spinning metal shaft, which restricts how much they can adjust. Achieving zero-compromise performance requires completely severing the mechanical chain between the pistons and the valves. This leads to fully independent valve control, where researchers are removing the camshaft and the traditional throttle from the engine block. In its place, every individual valve is equipped with its own dedicated electromagnetic or hydraulic actuator. The engine control unit acts as the digital brain, firing precise electrical pulses to trigger each actuator independently. These pulses snap the valves open and closed at extreme speeds. The mechanism is so fast, researchers compare the logic to operating a high-speed audio speaker. Internal combustion now functions as a software-governed process, trading fixed mechanical linkages for digital control. Using C# programming logic, engineers can now instantly redraw the exact depth and duration of a valve opening every single millisecond. Take a look at this data table from a 2025 study on composite electromagnetic valve trains. It shows a near 10% drop in NOx emissions and a 25% jump in low-load efficiency on single-cylinder tests. Because the valves aren't locked to a physical rotation, the engine can transition combustion modes mid-drive, switching from standard spark ignition to compression ignition on the fly. It even allows for firing sequences that are physically impossible to build with metal cams. Researchers are successfully running complex 12-stroke skip cycles to maximize fuel savings. Severing the mechanical link provides absolute authority over the combustion process. This cross-section highlights the physical risk. Without a camshaft, the mechanical safety net is gone. Valves and pistons share an extremely tight space. If a valve stays down a fraction too long, it's struck by a rising piston, a catastrophic failure known as valve-piston interference. Here, a single line of bad code, a microsecond of latency, or a slight voltage drop turns the engine into a self-destructing bomb. The final hurdle for a rollout in 2026 is writing the predictive control algorithms, like backstepping delay observers, required to manage this chaos. These algorithms must constantly calculate and compensate for electrical latency, sending the command to close the valve microseconds before it physically needs to move out of the way. The combustion engine is far from dead. By stripping away its mechanical past, it is being reborn as an adaptable, software-driven powerhouse ready for the future.